What is up, guys? Welcome to another episode of Casual Code Talk. Today we are going to be trimming the tree. Okay, let's pick our nice tree color. So trim the tree. This is a question I found on LeetCode, and I thought it was very cool and very nice. So basically, this is kind of a what do you call it? It's not an alternative. Wow, what is the word? A different, it's similar to deleting a node in a tree, but it's a different type of, wow, what is the word? Different permutation, different, okay, let's look this up. This is what it is, search tree. What is the word for different, I hate thesaurus.com, but I'll just look it up. Different type, different breed, different category, different permutation. It's a modified version. It's an altercation. Okay, whatever. So basically in this problem, instead of deleting a node, a single node with a value, what you're going to be doing is deleting all the nodes in a certain range. So one way to naively do this would be to use the delete node function and just call it on all values 0 to the number you want. But that is way overcomplicating things. The trimming tree, so basically, well, I'll write this out. Delete nodes in, or I think it's actually out of range. So there is a very nice way to do this, and it's so much easier than actually just deleting a node. So, okay, so let me start off by telling you what exactly you're returning. So you're going to return a tree node. So this is like deleting a node. You return a tree node. So keep that in mind. You are going to have to do something recursively. So trim, and then I'll give you the root, and I will give you start, int start, and int end. This is the range. Actually, I'm going to call them something else. High and low is nicer. High and low. Okay, so the reason why this is a lot easier is if you're at the root, like if you have a tree like this, and then like a whole big tree here, whole big tree thing here. Actually, that was a bad way to represent this. Let's say you have whole big subtree here, whole big subtree here. If your value at this root is greater than the high, if it's greater than the high, so let's say range is 10 to 20, and this is 25 here. What does that mean? What does that mean? Well, that means this entire subtree plus this node gets deleted. So then can we just return this? Well, not quite, not quite. What we can do is if, it's close though, if the root value is greater than high, the high value, what we can do is not just return the root's left side, we can return a trimmed version of the root left side, and then keep passing high and low, just like that. So if the value is higher than the highest, then we can return a trimmed version of that. And what this is going to do is, let's say it's still, let's open up this subtree here. Let's dissect it a bit more. let's say it's 24 here and 19 here and 26 here. Or wait, no, I can't. Can I do that? No, I can't. Because everything in this needs to be less than 25. Okay, let's say this is 23, this is 19, and this is 24. This is 19 plus a whole subtree here. Okay, and then it gets to 23, so it's going to return the trimmed version of the left subtree. So this value is still higher than it, so then it's going to return this part of it. Okay, so the point I'm trying to make is you can't just return the left subtree. You got to return the trimmed version of the left, because the left side could still have elements that are greater than 20, and they might also be less than 10 also. But yeah, there definitely could be also greater than 20 as seen here. They could both. It's guaranteed, these are guaranteed to be less than 25, but they could still be greater than 20. But let's say we get to here and we get to 19 as being the root. Now everything here is going to be less than 20, so now we have to, and this is actually the only place that could be less than 20, right? Because it's not like if we take a turn here, we go to 26, we can't get 20 here because this whole subtree needs to be greater than 25. So this is really the only place that's less than 20, and this algorithm so far has led us to the right place. And now we also have to focus on, let's say we get to 9 here. What do we do? So if the root val is less than the low, okay, so if it's less than the low here, so let's say we got here. Actually, this is skipping a case. So let's erase this here. Whoops, not the eraser. It really feels like I'm erasing stuff. Oh, not yet. Okay, let's say we started off with 9 here. I don't want to get to this case where it is in range yet. I want to first do out of range. So then we have 9, subtree, and subtree. So if the value 9 is less than our lowest number on the range, then what do? Well, we just return the trim root, the right side, because we know it needs to be greater than that. And then we keep passing in our high and our low. Okay? Notice how we are using our return value to our advantage. We're just returning the root of this subtree such that everything in the root is less than, or is in this range. Okay, so now the final case, else if it root value equals the value, what are we going to do? So let's say we have, let's make this 19. What do? It's in the value range. It's possible that everything here is in it, and it's possible that everything here is in it. But what's guaranteed is that the root is in it. So what we do is we say root, we know the root is in it. So what we're going to do is we're going to get the root left to be the trimmed version of the left tree, because the left side could go under range, right? We know it's not going to be over 20 ever, but it could be under 10, and we might want to chop those branches off, you know? Chop those parts off. So we're going to go root left and high, low. We're chopping off all those branches on the left side, and then the root right gets a similar version, a trimmed version of the root's right side, because it could go over. We know it's not going to go less than 10 here, but it could go over 20 there. High and low. And then after we do that, we can return the root, right? After we've modified its left and right tree. We are definitely returning this root, this one here, but we are modifying these subtrees because these subtrees could have values to be deleted. And that's actually it. We could look at the answer that I did here. Yeah. Oh yeah, and of course we also have to deal with that. Okay, but whatever. I just want to draw some parallels between this and delete node. So parallels, because it's basically a different version. That's the word I was looking. A different version of delete node. The similarities are that we are returning a tree node to a root that is trimmed here. Versus in delete node, we are returning a root to a tree or subtree that has that is the same as the original minus the node that we wanted to delete. And that became very useful, that it returned the tree node to the subtree that's trimmed, or the tree node to the subtree that deleted that specific node. In this case, when it wasn't the node to delete, which is here, when it was not the node to delete, we have to, what we do here is we make the root left equal the subtree on the left side that's trimmed. What we do in deletion is, if the value is less than our root's value, we say if it's less than, so if the value is less than our value that we have on the root, then we say the root's left side gets the subtree of the root left. It gets the left side subtree without the node that should be deleted. We're deleting the node, and after we delete it, we're returning that root here. Similar thing happening here. We're trimming the left side tree and returning the root there. This is a very common in recursion, and I hope you guys try to grasp this concept. It's hard to explain, hard to understand, but it's very important how you leverage the return type of your recursive thing, and how deletion of a tree node and trimming a tree are similar. And namely, that similarity comes here when we are leveraging what we're returning. Okay, that's all I have for you guys today. Hopefully you relaxed and enjoyed this casual code talk, and I will see you next time.